Hi, this is my video number 29. We actually comes to the end of our lecture. I just need to cover the volume integral and the Gauss theorem, the last topic that I will cover. So basically I just need a couple of hours, maybe 2 or 3 hours, yeah, or maybe less. So for today's lecture, I will discuss on the volume integral or triple integral. Yeah. So we might finish early. Maybe this is week 10, week 9, or maybe week 10. Yeah, week 10. So maybe we finish much earlier than expected. Yeah. So we have now on volume integral or triple integral. Okay, so what is a triple integral? We find the basically if you have a region, all right, let's say we have a region, let's say that, or yeah, so where we call this if you take part of it somewhere here with delta x, delta y, and delta z. So for that small volume, we have, let's say, delta v as represent the small volume there, can be written as delta x times delta y times delta z. So if you want to find the whole entire volume of those region or cubic bounded by those boundary, yeah, this is let's call this as a region T. Okay, the whole region there as a D. So to find the volume of those, what we need is that we have many small pieces here, yeah, where we split this into many sub-interval in x, y, as well as z direction. So we just need to add up all the small pieces, then it gives us the approximate volume of those region. All right, and then we take the limit of, let's say, this we cut into n sub-interval for x, for y into m sub-interval, for z, say for example we have k sub-interval. Then we take a limit, those m, n, and k goes to infinity. Then all the summation will become as an integral, or the approximate of the integral. Alright, so all this theory or fact that is just similar to the case of a single integral or double integral using Riemann sum that we have discussed in my video, in my previous video. Alright, so I think no need for me to go further on those limit and everything. You just give what we need to do. So let's just assume that. So basically, if you find the integral, so let's say let's call that we find the volume D. This is given as we integrate over the function f x, y, z, yeah, dv. So we integrate this over entire volume there. So then and our f basically covers that surface. This is our f, z, and it gives the, basically this gives the density, yeah, it gives the density with f different than 1, yeah. So density value per unit volume, right? And if you take if you take f equal to 1, then this gives us a volume to that surface, volume of D. Okay, and I'll give you some example. Not much theory we have here, just example. And also the example is not that difficult because everything covered in the most important thing is that how do we find the limit of integral, and then we can integrate that iteratively, inner, then a little bit outer, and the most outer integral. So let's say example, find the density for function f x y z equal to xyz, and D is a cubic. We have x equal to 2, y equal to 2, and z equal to 2. So let's see the region that described by that surface. Let's describe those things. So we have x equal to 2, y equal to 2 here, and z equal to 2. So basically we have that cubic. Alright, and then to find the density, what we need to find, this is our region D basically, and to find the density, we integrate triple integral over the entire region D, and then the function itself is xyz, f x y z D, to find the triple integral. Then this gives us, okay, so look at you can integrate, make it the outer integral, x, say, alright, so x is from 0 to 2, this is 2, this is 2, and 2, x from 0 to 2, so we have x from 0 to 2, and we have y also from 0 to 2, and we have z also from 0 to 2, 0 to 2, and then our integrand or function is xyz, and then we integrate over z dy dx. So if you solve this, so what we have, that will give you x equal to 0 to 2, y equal to 0 to 2, and then for z we have x y z squared over 2, 0 to 2 dy dx. Okay, so if you proceed this, what we have, integrate x 0 to 2, y 0 to 2, that give you 2 squared, 4 divided by 2, you got 2, so you can take out those 2 in front. What left is that x y dy dx. And then if you do this again, you got y squared over 2, and the limit from 2 to 0 to 2, again you got 2, you got 4, and then you get for x, you got same value, then you got 8, so total you got 8. So that's your answer. So pretty simple. It depends very much on the surface or on the region given. Some region is quite difficult to describe. So let's see other example. So let's say Okay, let's say I evaluate the yeah, another example. Evaluate the triple integral over the region D with the integrand is xy squared plus yz cube dv, where D is given as all the point x, y, z such that x between -1 and 1 and y 3 to 4, y 3 to 4 and z 0 to 2. So if you look at the region D, this is just a rectangular, just a rectangle, or a cuboid, not cubic, so not a cuboid. So again, the limit of integration is not difficult to be determined. So you just take x from -1 to 1, y from 3 to 4, z from 0 to 2. So in this case, you might no need to sketch the region. Yeah. So we just evaluate those things. So what we have is that so integrate x from -1 to 1, we integrate y from 3 to 4, then integrate z from 0 to 2, and then our function given as xy squared plus yz cubed, then we have dz, dy, and dx. Okay, then we integrate this iteratively. So what we have, x from -1 to 1, y from 3 to 4, and then we integrate z, so we have xy squared z plus y z4 over 4, z from 0 to 2. So what left is dy dx. Okay, so evaluate those the inside of those, inside of those integrals. So we have x -1 to 1, y 3 to 4, then we have x squared 2x squared 2xy squared, z is 2, plus, so we have z 2 to the 4, we got 16, 16 over 4, we got 4, so we have 4y, and minus z give you 0, that dy dx. Okay, and then evaluate again. For the inner integral, we have x -1 to 1, integrate respect to y, so we have 2x y cubed over 3 plus 4y squared over 2, so we have 2y squared, where y from 3 to 4, right? So dx, and this will give you integrate x from 1 to 2, from -1 to 1, so this is -1, this is -1, -1 to 1, y, 4 to the 3, 64, right? So we have a and then alright, so we have 64, 2x squared, 2x, that 4 cube over 3 plus 2 4 squared minus 2x 3 cube over 3 plus 2 cube 3 squared dx. Okay, and then the rest I think you can solve this. Just need a couple of steps there, then you should get the solution is 2028. Alright, so let's go to the more difficult diagram. Let's say if I have another example here, given f xyz as a xyz, and your region D, let's say defined by this diagram. So we have let me write that our region D, z is 4 minus x squared minus y, z equal to y, and what else? I think so we have x for yz, for xz, y is 0, so we have those things, 4 minus x squared, so basically we have something like that. So we have 2 here, so we have 4, okay, in the first octant. So the negative part we don't take into account because we just need the first octant. Yeah? And then we have for this yz equal to 0, so we have z equal to 4 minus y. It's just a straight line, alright, with a negative what we call that, slope. Yeah, so we have just that, okay, and then cut by that. So you can also have the yz, xy, where z is 0, so we have y equal to 4 minus x squared again. So basically we have something like that. So basically that's your surface, okay, and cut by z equal to y. Yeah, z equal to y, this is a plane, z equal to y. So z equal to y is, we have like that. Alright, so your surface will be like that. Okay, so that's your surface. That. Okay, just like a piece of watermelon. Yeah, like a piece of watermelon. Now, for this we need to determine what is a limit for x, y, and z. All right. So let's do this. If you look at this from z positive, so surely that line will fall somewhere here. So just look like that. Okay, and this line is given as y equal to 2 minus half x squared. Not difficult for you to determine those things. Just solve these two equations, then you can have what y is in term of x. Alright, so then the integral over those region d of f xyz dv, that give you, we integrate basically over r, where our r is here. Yeah, this is our r, and z, our z is from y to that 4 minus x squared minus y, and our function is xy z dz d r there, or also x and y, of course. Okay, so for x and y, so you can see x from 0 to 2, so this is integrate x from 0 to 2, and y you can see from 0 to that line, that curve. So we have y from 0 to 2 minus half x squared, and then we have z equal to y to 4 minus x squared minus y, xy z dz dy dx. Okay, so having done that, the rest is just need to evaluate this or integrate this iteratively. So consider the most inner integral. So that gives us, so let me bring it a little bit to the left. So we have x from 0 to 2, we have y from 0 to 2 minus half x squared, and then inside there we have xyz squared, xy z squared, z from y to 4 minus x squared minus y dy dx. Alright, so that give us integrate x from 0 to 2, y from 0 to 2 minus half x squared. Then we have this one is xy z squared, so we have 4 minus x squared minus y squared minus z squared over 2. Z squared over 2. So this is over 2. I can put it 2 is there, or you can take it to half to the outside of the integral. And then we have z squared y, so we have y squared here. dy dx. Okay, so from now you can just proceed with how to solve this, right? So you will end up with the solution which give you, or should I solve this part? I think this is easy. So you can have 4 minus x squared minus 2 4 minus x squared y plus y squared, that part here, and then minus y squared, and then minus y squared. Okay, that give you, let's cancel out. So here you can again open up this bracket, so have 16 minus 8x squared plus x squared, and this you have minus 8 plus 8y plus 2x squared y. Alright, and then so what left is that this is so we have 16 minus 7x squared minus 8y plus 2x squared y. Okay, so then this is easy for you to evaluate. So the solution is 32. This is what I have. You can check this. Yeah, 32 over 15. All right. Of course, I have some more example here, but it's just almost not really similar, but you just need to determine the limit of integration, then done actually. Yeah? So let's try one more. Okay, find the, again example, find the value of the region bounded by z x squared plus 3y squared and z equal to 8 minus x squared minus y squared. Okay, so if you can recon this, what is this actually? This give you okay, let's sketch those. Okay, so you need positive and negative. So what is this? This is, just look at on the xy plane first. Look at on xy plane. For xy plane, so this is z equal to 0. So what we have, x squared plus 3y squared is 0. Then that gives you not much information on that. Okay, so but if you increase this z equal to 1, z equal to 2, z equal to 3, so what we have basically what you call those things, like a cone, not cone actually, like a cup, yeah, open cup, just like you have something like this. All right, 0 is here. This point here, it is here. Yeah, this point here is here. So you got something like that. And for this, you have something like that. So if you put them together, those things, so what we have is something like so let's do this. How can we do this? Sort of that, like rugby ball, right? And those will be projected on xy plane. So you have that on the xy plane, that curve, okay, that projected on the xy plane. So you have those, right? So how to find this curve is by solving those two equations. All right, if you solve those two equations, so what you have there, z equal to z, so we have x squared plus 3y squared, this is equal to 8 minus x squared minus y squared. All right, so what we have, x squared, 2x squared plus 4y squared, this is equal to 8. So this is a ellipse, right? So this is ellipse on that surface. Now, then we can evaluate this. Of course, if you look at this two equation here, this one of that form, this one of that, so surely that function or that surface is smaller than that surface, because we cover all those things. So we evaluate over z from that surface to that surface. Okay, so therefore we have our integral. Another thing is that we need a volume integral. So for volume integral, we have, let me write somewhere here, we need f is equal to 1 for volume integral. Alright, so which means we just need to integrate to find the volume, is that integrate z from those surface, which is x squared plus 3y squared, to the that surface, which is 8 minus z. Okay, so 8 minus x squared minus y squared, and this function is just one, so we have d z dy dx. And this region R here, you solve these two equations, you have those. You can do this by using transformation, of course, if you want. Okay, so just divide through by you can divide by 4 or by 2. If you divide by 2, that gives you x squared, yeah, x squared over y squared, y over 2 squared, yeah, so 2 squared, that gives you 4, so 2 squared. Alright, so then this what we do here is that from those ellipse we transform into, where can I write? We transform into on xy that a circle. So let's say u and v. So how to do this? You just take u equal to x, y equal to y, v equal to y over sert 2. So then you transform those equations into u squared plus v squared equal to 2 squared. So this is a circle. Then you can use the polar coordinates, right? So where your u is r cos theta, your y is r sine theta. Then of course here you have again this is v should be, and then again here you have du dv, this gives you r dr d theta. Yeah, because once we do that transformation of, this is for the second integral here, because after the first integral, the inner integral here, after that you have let's say I put this r, let's say I put that r. Okay, so then we integrate this is over r. Okay, now integrate those over r. Then here, after doing that integration, we have a minus x squared minus y squared minus x squared plus 3y squared dy dx. Okay, and then from there we have again integrate, try to simplify this. We have a minus 2x squared, and then you got minus 4 y squared dy dx. Okay, then we do that transformation, u equal to x, y with that, v with that. So what we have, that will give you integrate over r, and then we have a minus 2x is u, so 2u squared minus 4y squared. You can write this as squared, so we have v squared of 2v squared, right? 2v squared. So right, so we can have y as a sert 2v. So y squared give you 2v squared. So we already have 4 here, so we have 8 v squared. Okay, so for dy, so we have sert 2 dv, so we have sert 2 dv. For dx, we have du. There. Alright, and then do that transformation again using polar coordinates. So that I think that will give you much easier way to solve this. So then we integrate theta from 0 to 2 pi. We integrate r from what? That with the radius, this a circle with radius 2. So which means r from 0 to 2. Yeah, r from 0 to 2. Alright, and then we have a minus 2, our u is r cos squared, so 2 r squared cos 2 squared minus 8, our v is r sine squared, so r squared sine squared theta. Then we have set 2 here. I can bring it in the front, so let's say I put it here, set 2. Then we have dv du that give you r dr d theta, r dr d theta. Now you can solve this. Of course, here r squared you can factor out, and what left is cos squared and sine squared. You might not be able to find the identity directly, which is cos squared plus sine squared equal to 1. You cannot factor. You cannot use that one, but you can use the other identity. Like cos squared is half 1 plus cos 2x, and sine is half 1 minus cos 2x. Use that, and then you can solve this problem. Alright, so I leave this part to you. Then we end up with the solution would be, yeah, we just give you the solution to you. You have the solution is given as 8 pi sub 2. Alright, of course from here, if you don't want to do the transformation, if you don't want to do the transformation, especially this part here, then the integration would be from 0 to, you need to write our y, where is it, here, from here, y in terms of x. So you have a sort of y equal to plus minus 1 over 4 square root. So we have 1 over 2 square root 8 minus 2x squared. Yeah, you need to use this here. So from minus half square root 8 minus 2x squared to the positive, yeah, plus half 8 minus 2x squared. For that round is much easier for you to do, but when you want to integrate for the x, then that's involve a square root. It might be difficult for you. That might be difficult for you. So the best thing is using the polar coordinate, but you need to transform. So what I did, again, I recap this. What I've done here is that from the given question here, we find the region, try to sketch those region, and then those region, we know that it does involve triple integral. Then on the we can always look at the z positive, and then those region projected onto xy plane, where you obtain the region R here. So the region R here you have in terms of a what we call those ellipse. All right, those ellipse, and then those ellipse we transform into a circle. Those transformation, you just follow that. So this is what I did here. Then you can solve the rest of it. Okay. All right. So that's the example. Okay, I give you an exercise, yeah, to think. I give you an exercise for you to think. First, try to look at the region, and then try to identify the region, sketch if possible, and then from there you can determine the limit of the integration. Yeah. find V volume. Let me write those. Volume of a solid bounded by the cylinder y equal to x squared, and this is and plane. This is not cylinder, right? This is not cylinder, just ignore those things. Bounded by this line y equal to x squared plus a plane plane y plus z equal to 4 and z equal to 0. For this I have a solution. The answer is that 256/15. Okay, of course I have some more if you want. Let me try to look at this. Remember that we have a volume here, yeah? We have a volume. Let's try to find other example. Okay, let's say we want to evaluate this triple integral with x y squared plus yz cube. This is our region D, dV, where our region D is given as okay. So our region D is given as, we have z equal to 3x squared, z equal to 4 minus x squared, 4 minus x squared, y equal to 0, and z plus y equal to 6. That's your region. Okay, try to evaluate and find the limit of the integration. Okay, before I stop for this video, let me give you a couple of properties of the triple integral. Yeah. This is just simple, no need to prove basically. Properties of the triple integral. So if f of function x, y, z and g is x, y, z, both are integrable in some region D, then we have integrate triple D k f x y z dv. This is, you can, for any constant k, you can factor out those k, and then what we have, df x y z dv for any constant k. Okay, and then number 2, we integrate d k f x y z plus minus g x y z dv. That give you, we combine the first properties here, and then we have k integrate over d f x, y, z dv plus minus, yeah, if plus plus, if minus minus, yeah, respectively. So we have k d g x y z dv. And then number 3, we have integrate over d of f dv that give you positive if f is positive, yeah, in the region D, in D. Number 4, properties number 4, we have integrate over d f dv. This is always greater than integrate over d g dv if f is greater than or equal to g in D. This example exactly as we have discussed in the previous example, these properties here, where we take the limit of integral from the smaller function to the bigger function, or smaller surface to the bigger surface. Right, so that's number 4. And number 5, we have, if you have D is you have many of di, so I from 1 to n, see, then those integral over d f dv is just, we integrate just summation all those things, I from 1 to n, integrate di f dv. Okay, so with those 4-5 properties, I think that's all for this video. Let me recap what we have done. Basically, triple integral is not difficult to solve. What important thing is that you need to identify the limit of integrations. Yeah, once you do that, then the rest you should have no problem to solve. So with that, I thank you. See you in the next video. Bye.